This photograph shows rushing white water discharging through a concrete spillway at a massive dam site. But how does that physical rush of water translate into the electrical power currently charging the device you're holding? That falling water provides the mechanical force needed to rotate magnets past copper coils, a process that forces electrons to flow through the national grid. This interaction is the science of electromagnetism. To understand how a massive national grid operates on a macro level, we have to scale down and see what happens invisibly inside a single piece of copper wire. This diagram demonstrates the core principle. Whenever an electric current flows through a wire, it automatically generates an invisible magnetic field around it. We predict the direction of these field lines using the right-hand grip rule. If you point your right thumb in the direction the current flows, your curled fingers follow the exact path of the magnetic field. Because electricity naturally creates this magnetic field, we have a tool to turn a magnet on and off with a simple electrical switch. This setup explores the reverse scenario. We place a current-carrying wire inside a pre-existing magnetic field. The wire's circular field interacts with the magnet's straight field. On one side, the fields reinforce each other and get stronger. On the opposite side, they cancel out. This imbalance physically pushes the wire from the strong side toward the weak side. We map this three-dimensional interaction using Fleming's left-hand rule. Your first finger points from north to south, your second finger points with the current, and your thumb reveals the resulting motion. Converting electrical energy into physical motion is the exact mechanism powering every electric motor in existence. We can also run this process in reverse through electromagnetic induction, sometimes called the generator effect. Here, we use physical motion to create an electric current, like in a bicycle dynamo. As the magnet spins inside the coil, the magnetic field constantly changes. This shifting magnetic flux physically drags the electrons along the wire, inducing an electrical current. You can feel this physics in action when using a bicycle dynamo. As you switch on more lights to draw more current, the pedals become noticeably harder to push. Lenz's law explains that the current we just induced creates its own new magnetic field. This new field is oriented to oppose the change that created it, meaning it actively pushes back against the spinning magnet. Generating energy requires effort. You must continually exert physical force to overcome the opposing magnetic field you are creating. This photograph shows an industrial electrical transformer. We rely on these devices to step the voltage up or down to manage it across the grid. This diagram reveals a transformer's internal structure. They work entirely on the principle of electromagnetic induction, meaning they rely on a changing magnetic field to function. Direct current, or DC, produces a flat, steady magnetic field. Because nothing is changing, no current is induced. Alternating current, or AC, constantly shifts direction, providing the continuous fluctuation needed to induce a new current in the secondary coil. This table provides the formula to calculate transformer ratios. You have a transformer where the primary coil has 100 turns and the secondary coil has 500 turns. If your input voltage is 100 volts, pause the video and calculate the output voltage. We plug our numbers into the equation. The secondary coil has 5 times as many turns as the primary, which means the voltage increases by a factor of 5. This is a step-up transformer, outputting 500 volts. By altering the physical ratio of wire coils, transformers allow us to multiply or divide voltage across the grid. This image shows a long row of electricity transmission towers. Power companies use step-up transformers to send electricity across long distances at extreme voltages, often around 132,000 volts, rather than the standard 240 volts used in your home. This math traces transmission lines connecting cities across Uganda. When electricity travels these vast distances, power is lost as heat, calculated by the formula current squared times resistance. Because power loss scales with the square of the current, keeping the current low is critical. By stepping the voltage up incredibly high, the current shrinks proportionally, preventing mass amounts of energy from burning off as heat in the cables. Our ability to manipulate magnetic fields allows us to generate mechanical power miles away, convert it to electrical energy, and deliver it efficiently to cities across the nation. We use the motor effect to create physical motion, the generator effect to produce electricity, and transformers to regulate voltage throughout the journey. To continue practicing these calculations and explore more physics topics, visit the Yaka Digital Network at www.yaka.cc.